Okay, I'd like to welcome you to the first of the two afternoon sessions. We're just waiting until the audience becomes a little less compressible. First talk in the session is by Volkan Cevher from EPFL, who's going to talk about clash.
Thank you, Robert. I'd like to first thank the organizers again, in particular Larry and Becca, if she's around. So today, my talk will be about a quintessential example of acronym-driven research. I'll be talking about the combinatorial selection and the least absolute shrinkage algorithm, which I call it as the clash operator. By the way, can you hear me? No. How about now? All right. So maybe this is too much. How about that? Good? Let me do modulation myself. All right. So, okay. I mean, I'm preaching to the choir here when I talk about linear regression problems, so I will be brief about this motivation. Many problems in signal processing, machine learning, and communications can be cast as a linear regression problem, right? Where an unknown vector x is related to the observations through a matrix. Just to set up the notation, we'll be talking a lot about an unknown vector x, which will be in n dimensions, observations u in m dimensions, and a matrix phi m by n. This happens in compressive sensing, where you try to design a sensing matrix to reduce the cost of your measurement process. In examples like machine learning, this matrix is a God-given matrix of your features, where you try to understand the output in terms of these features. In theoretical computer science, this problem happens when you want to take a sketch of your vector, right? Because of his theoretical interest, as well as practical interest, we focus on the underdetermined case, which is very challenging. And the challenge is due to the fact that the matrix, when it's dimensionality reducing, where m is less than n, it has a non-trivial null space. So any vector in the null space of this matrix added to the true vector will give rise to the same measurements. So clearly, we need some prior information to distinguish the true vector among these infinitely many solutions to this regression problem. And approaches to incorporate this prior information, you can basically split them into two distinct camps, where you can think of one using deterministic approaches, the other one following probabilistic assumptions. In the deterministic camp, what people like to do, they like to assume things like sparsity and compressibility, and then they look at the problem, they try to use certain norms to distinguish or separate good things from the bad vectors. And in the probabilistic camp, what you do is you assume a measure in the space of the unknown vector, and then you use maybe the likelihood under the chosen measure to distinguish two different vectors, right? Surprisingly, there's only a few connections made between these two seemingly different frameworks, and this is certainly an interesting one. However, we're going to take a deterministic path today and describe things from a model-based compressive sensing view. So who knows about compressive sensing? Okay, so I assumed that much, and I basically skipped the backgrounds on compressive sensing. I'll just give certain definitions so that I'm consistent throughout the presentation. So a general vector in n dimensions can be anywhere in space, right? But we'll be talking about k-sparse vectors that has at most k non-zero elements. If you think about these vectors, they live in these k-dimensional hyperplanes that are aligned with the coordinate axes. So just to give you a visual example, here is a two-sparse vector, the set of two sparse vectors in 3 dimensions, and you have these hyperplanes that are aligned with the coordinate axes, right? And many times when I talk about the support of a vector, I'll actually mean the indices that correspond to the non-zero elements. And when I say x, for example, an element of sigma k, that means X is a k-sparse signal. All right. So let's talk about what made compressive sensing famous. Tractable algorithms, right? If you think about this linear regression problem and you assume sparsity, meaning you have just a few number of non-zeros, people, have been talking about the Occam's razor kind of approach where you say, the sparsest solution is the correct one, right? However, so that would correspond to an optimization problem, like you have certain measurements, you want to find the sparsest solution that explains the measurements. This is an NP-hard problem, which you have to go through a lot of combinations to figure out which are the sparse coefficients. An incredible insight turns out to be that if you convexify this L0 norm, which basically counts the number of non-zeros, and replace it with the L1 norm, you actually get the true solution, right? So yesterday, if you were at Ben Recht's talk, he had this animation where he grooved this L1 ball until it touched the constraint space. In this case, it's like a line, right? I would like to bring your attention to the following subtle issue, though. When we give this example, we always show just one side of the picture. Now, take a look at this. Here, it's the same problem where we were picking a sparse solution. Now, let's look at the original problem. We have this constraint, which is a hyperplane, so to say. And there are two one-sparse solutions. So I'd like to ask, which one is the correct one? So if you think about the basis pursuit solution, there's a unique solution, right? We pick this guy. But if you look at this, there are two solutions. And they're both one-sparse, right? So this is the kind of example where people who work on greedy algorithms like OMP, bring out to the table to say that, this is where basis pursuit fails, right? And this is the kind of situation where, if you run an orthogonal matching pursuit kind of algorithm, you would pick, for example, this larger coefficient first, and it may terminate. And it's not necessarily the correct solution. And in particular, if you, look at the audience here, many of them worry about designing sensing matrices such that this never happens, so that when you run the convex algorithm, it'll give you the correct solution. The reason I gave you this example is to highlight the fact that this L1 ball, its geometry, inherently gives you sparse solutions, but at the same time, it also gives you information about the norm of the signal. So in this particular example, if you look at the two one-sparse solutions, basis pursuit inherently also picks the one that has the minimum L1 norm. So there are two kind of bonuses that you're getting when you use, for example, the basis pursuit solution. One, the inherent sparsity, and the other one, the norm of the signal. Right. So when I look at the sparse recovery algorithms, I create three categories. And the first category is the combinatorial category, where you end up using these non-convex constraints. And the famous model is the union of subspaces model, where you have a certain union of k-dimensional hyperplanes. And the algorithms you have typically try to minimize the cost like this. You have the data error in the 2 norm. You minimize with respect to your non-convex constraint. In the geometric approach, in the second camp, so to say again, what you do is you look at the tightest convex relaxation of your set, and you use concepts like the atomic norm concepts, which were discussed yesterday. And then, in this case, you, for example, end up using the Lasso formulation, where you try to minimize the data error subject to one norm constraint. And the third example is always, you have these probabilistic relaxations, like to call them the compressible priors, and then you can actually motivate algorithms based on, variational inference arguments, posterior mean estimates, and so on and so forth. So clash, where clash falls within these different optimization frameworks, it basically combines these two approaches. And this may seem redundant, but I will try to make a compelling argument that this is not at all redundant, and it actually gives you the best of both worlds. Now, in order to introduce the key actors that make clash very interesting, I would like to tell you a story of two seemingly different algorithms. The first algorithm that I will tell you is the famous soft thresholding algorithm. Now, let's start with the following. Let's define an objective function, which is the L2 data error, quadratic L2 data error. And let's look at this objective function. We have this one norm constraints, and let's say we have a feasible point that we can start within the constraint set. So what we first do is we note the following the structure in the optimization objective, which says that if you take a point and then put the supporting hyperplane, the tangent hyperplane under the cost function, the distance between the cost function to any point on the hyperplane is basically a quadratic. Given this, what we can do is actually create a nice quadratic upper bound by taking the hyperplane and maybe using the spectral norm of the matrix and coming up with this nice expression. And then a straightforward idea is that, okay, suppose we're at a point, we create a quadratic upper bound to your objective function, and we try to minimize the quadratic upper bound. Remember, if the original problem was easy to optimize, you would have done it. However, by coming up with this quadratic upper bound, you come up with a problem that you can easily solve. And because it's an upper bound, the minimum of this is you move, you always improve your objective. Okay, and it turns out that the minimizer of this quadratic upper bound for this particular problem is this least absolute shrinkage operator, right? And there were many discussions about this yesterday. Now, here's an interesting thing. You can, in this setting, you can always overestimate what people like to call as the Lipschitz constant. In this setting, you can do this iterative optimization procedure. If you overestimate, you would just converge to the true solution, but you would be slower, right? Now, then the key question here is that you would like to figure out when you terminate this algorithm whether or not you actually have the correct solution to the original problem. So what people tend to do, they like to assume certain local conditions in the optimization objective, such as you look at the dual certificate of your problem on the support of the signal, and then you come up with certain local conditions that you assume. And these local conditions, because it's a convex optimization problem, implies global optimality. And you basically say, okay, if these conditions are satisfied, my algorithm will give us the correct solution. Now let's take a look at the same story and say, all right, as opposed to doing soft thresholding, let's try to do hard thresholding. Okay, this is where the common, these greedy algorithms or the hard thresholding algorithms come in. Now, the idea here is this. Suppose you start with a k-sparse vector, you put the same quadratic upper bound, and you try to do this optimization over these non-convex constraints. And the interesting thing is that the minimization of this quadratic upper bound actually can be exactly done with the non-convex constraint. So if I give you a vector, and I ask you to find me the best k-sparse approximation to this vector, it just corresponds to sorting the coefficients in terms of decreasing magnitude and then picking the largest k, right? So you can start with the same idea. You say, I am at a k-sparse vector, I do my gradient update, and then I will go to the minimum of this quadratic, and then I will iterate so that I will go to a k-sparse vector that minimizes my objective. So what could be wrong with this naive proposal? The thing that can be wrong is that you're no longer doing optimization on a convex set. So the set on which you're trying to navigate has percolations, right? So you can easily fall into a situation like the following. We're at a point, feasible point. You put your quadratic upper bound, but there is no other k-sparse point below this quadratic upper bound. And even if your gradient is telling you to go to a certain direction, your quadratic upper bound curls up, and it evaluates a point which is better than your original point in terms of the objective function. The upper bound says that's a worse point, so don't go there, right? You can immediately get stuck at solutions like this if you're not careful about how to choose, for example, your Lipschitz constant. It turns out that if you want to guarantee the convergence of such a scheme, you need to end up assuming some global structure of the optimization problem. And the most common assumption is this restricted isometry property, which says that your matrix acts as a near isometry to all k-sparse sets, meaning it takes these k-sparse k-dimensional hyperplanes, maps them into other hyperplanes, and the distances between the points are more or less preserved up to an isometry constant delta, right? And, you know, people show that if you use random matrices, this property is satisfied with overwhelming probability if m is something like k log n over k. And then given this, you can go back to the original algorithm and derive a condition on this isometry constant so that you can basically tiptoe on these percolations while never, you know, stopping because there's like a large gap between your k-sparse points. So a few years back, we did this work with Rich, Marco, and Chinmay. And what we realized is that as opposed to just doing hard thresholding, you can do what we call as the model-based thresholding. And the idea is that in many cases, sparsity is a first-order model, and you have much more structure in the problem, like a correlations between the sparse coefficients that previous approaches, you know, did not exploit. And what we showed was that all you need to do is replace this projection operation, which was hard thresholding, with the model-based hard thresholding, and you would get the same kind of setting as just the simple iterative hard thresholding, right? This approach would converge and would give you the model-based signal. And the isometry requirements that you had necessarily go down because your model is more restrictive. And the salient example we had was this tree-sparse model where we assumed, for instance, as opposed to just having a k-sparse signal, we had a k-sparse signals lying on a rooted connected tree. And then you have that, you can prove that you just need something like order k number of measurements to have the same isometry constants. And we gave examples where we actually observed that when you try to do recovery with such a model, you get dimensional independent recovery, which was very nice. And the algorithm that we used was actually the condensing sort and select algorithm, which would give you the best K3 sparse approximation. Good. So just to put things into context, because you know there's a very wide range of people here who worry about this from the convex optimization perspective, so on and so forth. With Lasso, what people realized was that they saw this geometric interplay between the L1 ball and the L2 data error. However, like the last decade went into how to leverage additional information about your sparse coefficients. So when you run Lasso for a particular, for example, bioinformatics problem, you would get sparse solutions which would explain your data well. However, the results wouldn't be interpretable because the L1 ball gives you sparse solutions, but the selections it does is somewhat arbitrary. And then came people like Francis Bach, where they started to introduce this Lowash extension of submodular set functions to come up with these polytopes that have certain, gives you certain correlations in your solution, right? So that also, the idea is to customize a certain geometry by, for example, combining basic norms together so that you have the desired geometry that leads to solutions that are interpretable. And on this front, what model-based CS were doing was to exploit the combinatorics of the sparse solutions just to, exploit model sparse projections to give you solutions that were exactly sparse in your model space, but there was nothing about the geometry that they exploited. So the question was, can it exploit or can it not? So this is where Clash comes in, okay? So we're going to rack the Casbah now, hopefully. I think the best approachable introduction to Clash is this, just what it does, all right? So the codes are online. Just feel free to use them and send me back some comments. What Clash does is it does what the greedy algorithm does with some additional stuff, all right? So if you look at like a greedy algorithms, you would have a k-sparse set expansion. You would have some optimization on the set, then you would do some pruning and then do other additional things, right? When you look at Clash, there are two key things that come into play that turns the problem into the following setting. You have the L1 ball constraint, and now your hyperplanes don't extend to infinity, they get cut by the norm constraint. So here's the interplay of these two actors, so to say. The first actor is the combinatorial selection, which is these union of hyperplanes. When you apply these and the least absolute shrinkage operator, when you apply these things in sequence, you tend to approximate and give a geometry to your problem, which is this hold out L1 ball. And the neat thing here is that when you replace your hard thresholding operation with this model-based hard thresholding operation, you get this combinatorial origami of the L1 ball or whatever norm you're trying to do, which you can basically pick out certain faces and so on and so forth to get the desired structure. I would like to note here that if you have this problem and you try to convexify it again using these atomic norm ideas, you go back to the L1 norm. So there are certain models that cannot be directly handled by the simple convexification. So this brings me back to this combinatorial selection problem and basically the workhorse of this model-based CS approach. What I would like to say here is the following. It turns out, that we were saying when we presented the model-based CS, as long as you have this projection exactly, things were nice, right? But people did not know what projections would be exact. So here, what we showed is the following. This combinatorial projection can be nicely written as a set function optimization problem where the set function is modular. It means it can be factorized into simple terms over the indices. The moment you realize this opens the door to all these computer science structures where you can say whether or not you can solve this problem exactly or approximately. So here I would like to highlight one property that I will refer to later on. It's called the polynomial time modular epsilon approximation property. And the idea is that you have this modular set function which you need to optimize. And if you have an algorithm that gives you an epsilon approximation of it, meaning it will achieve 1 minus epsilon of the optimal solution, which could be combinatorial, then you can use such sets in this setting. So let's see which sets have this P map 0, meaning you can exactly get the solution. Matroids. I'm not going to directly define what matroids are, but just go and read. I will just give you examples. For matroids, you can think of uniform matroids as your regular sparsity. You can look at partition matroids like block sparsity or group sparsity with disjoint groups. You can look at cographic matroids, which tells you a clustered subgraph of any graph, basically, which could be something like the tree model or the group adapted Hull model of Francis. You can also have totally modular systems where you can try to enforce mutual exclusivity of your sparse coefficients. You can also have interval constraints to your sparse coefficients that you can exploit. So what models have PMAP epsilon? The most interesting one is the knapsack model, where you can define certain weights over your support and actually constrain discretely what value you get out of picking a coefficient. You can actually create such constraints easily by using a probabilistic model and using like the log probabilities of each group. You can actually come up with supermodular or submodular interactions between your sparse coefficients, which I believe will be very useful. But in the end, if you have an algorithm that gives you this epsilon approximation, you can define your sparsity using an algorithm, as opposed to this generic union of subspaces model. Now, I just would like to maybe get some feedback from the audience here. People talk about solving group sparse problems with convex optimization algorithms, and people say, we find the best solution, so on and so forth. I just would like to highlight the difficulty of the selection problem for group sparsity. And here, if you look at a group sparse problem where you have pairwise overlapping groups, it turns out that, let's forget about the linear regression. I give you a vector, which is a little bit noisy. And I ask you to select the best k group sparse subvector of this. This corresponds to a minimum cut problem with a cardinality constraint, which is known to be strongly NP hard. So there is some theory which is lacking here when we actually have a selection problem which is inherently very difficult, but somehow we convexify it and actually forget about this inherent difficulty. And this is something that I would like to understand. So here is the theoretical guarantees of clash. It's actually quite a lot of variables, but just the gist of it is the following. If you have inexact projections, it turns out that there is actually a minimum limit that you can approach in terms of the signal, which turns out to be on the order of the delta constant times square root of epsilon plus epsilon. If you don't have an epsilon, if you have epsilon 0, then the isometry requirement of this algorithm turns out to be 0.365, which is decent among the greedy algorithms. So let's give examples and end the talk. Here's an example where we have a severely underdetermined system, and we try to use lasso, we try to use the k-sparse clash, and we try to use this k-model sparse clash. And the first example, the sensing matrix is a adjacency matrix of a balanced expander, which is a sparse matrix which doesn't have RIP. This is just to show you that these algorithms, although you derive them for like with RIP assumptions, they do things that are meaningful. Here, when you let lambda go to large values, you actually get the model-based CS solution. As you decrease lambda, you end up getting the impact of the norm. So the thing that you will realize is the following. As lambda varies, the norm has a significantly positive effect on the recovery performance. And you can also have things like a partition model on your sparse coefficients where you put certain budgets into certain partitions, which could be useful. We applied this to Justin's compressive sensing CCD array readout problem, where we see that if you use something like this rooted connected wavelet tree, you can get improved SNR with just, with using very few sparse coefficients. We worked on comparing, group lasso with, group clash, where I don't know if we have an approximation algorithm. We just used like a quadratic program with rounding scheme. And we tested this scheme with knapsack examples, and there is actually quite a positive impact of knapsack. So let me conclude. What we did in this is basically combine the power of these norm constraints with the combinatorial constraints and gave an interesting sparse recovery framework. And the highlight is this PMAP epsilon sets, which basically tells you that there is an underlying difficulty in the combinatorial selection which directly impacts your recovery performance. And the key, again, thing here is that if you have PMAP, you know the underlying difficulty, you can actually leverage these combinatorial optimization algorithms which have provable space and time bounds, and they tend to be much better than just heuristics. And it turns out that our proofs are also applicable to other norms, such as the TV norm, where you can replace the one norm constraint with a TV norm constraint. So with that, I will end. Currently looking for postdocs. If you're interested in, please contact me, and I'll take questions. It was that clear, huh? All right.